Hello and welcome. In this video, I'll be talking about programming, what it is, why it's extraordinary, and why we should all learn it, regardless of whether or not it's essential for bioinformatics. I want to start with this quote. A new, a vast, and a powerful language is developed for the future use of analysis, in which to wield its truths so that these may become of more speedy and accurate practical application for the purposes of mankind than means hitherto in our possession have rendered possible. These words are by Ada Lovelace, and they were spoken in the mid-19th century. And when I see them, I still get shivers because it really shows how this person glimpsed the future in a way that none of her contemporaries did. Who was she? So she was an English mathematician, the daughter of a wild and emotional poet, Lord Byron. Her mother was so afraid that she would end up like her father, that she forbade her daughter from doing anything remotely resembling art or poetry, instead having her tutored in math. She became an apprentice to Charles Babbage. He was an eccentric intellectual who had created a mechanical calculating machine, the difference engine. And he had a design as well for a more powerful analytical engine, which would have been programmable like today's computers. So she took this idea of an analytical engine and became obsessed with it. And she realized that you could calculate all sorts of things, not just actuarial tables. And she's widely credited with having written the first loop. And she used this loop to compute Bernoulli numbers. So this was a real program. And she was the first programmer in the modern sense. The second quote here, it is possible to invent a single machine which can be used to compute any computable sequence. This is by Alan Turing, and he is the other kind of pioneer, founder of computing. And he really took things to a whole new level. So he conceived of a universal computing machine that became the basis for modern programmable computers and computing today. So what was this idea? What is a program? A program is a progression of states. You start with an input. This is an initial state. So an analogy is with cooking or baking. You start with some ingredients, flour, oil, sugar, salt, and you have a recipe, a series of steps or instructions with which to take that initial state and transform it into subsequent states. So you have intermediate states like, when you're waiting for the dough to rise, when you put the kneaded dough under the rolling pin, when you put the objects in the oven, and then you have an end state, the final product. And so programs do this too. You have an input, a series of steps that carry this initial state to an output or a final state. And Turing's idea was such a machine, and he conceived of an abstract mathematical device that would read a strip of tape. And on this strip of tape, you would have numbers written on them, ones and zeros. And the machine could, at any point in time, only read one position on that tape. And it had in its data banks a set of tables or instructions that told it, if you were located at position, say 353, and you were looking at a 0, then convert that 0 into a 1 and move to state 15, for example, and would have these instructions for every position. And that's it, and until it reaches some sort of halting state. And that was his idea. But it turns out that this extremely simple idea has since been equated with the modern stored program architecture that's the basis for today's computers. So let's talk about the history a bit. So Lovelace and Turing, they were not the only people to contribute to where computing is today. Computing is one of those things that there's no single inventor, and I think it really represents innovation as it occurs today, because things are hardly ever the result of one person anymore. And so let's walk through some of its history. So of course we'll start with Ada Lovelace and Charles Babbage, the first to kind of come up with the idea of programming. in this universal sense. But not much else was happening at this time. You have, at the end of the century, many years later, George Boole comes up with an algebraic system of symbolic logic. The idea of true and false. If A and B are true, then C is false. And it sounds very simple, but no mathematical framework for this kind of thinking had existed prior to him. And more time passes. So this was 1890. A lot of time passes, and really, no revolution was sparked right after these people or during their times, unfortunately. But then in 1935, kind of in the shadow of the lead up to World War II, you have Tommy Flowers inventing the vacuum tube. And this is just a simple on-off switch, a physical switch, an electric switch. But this later turns out to be the key piece of technology that enables Boolean logic and enables the logic that is the basis for computing to be conducted in the physical realm. And it was Claude Shannon in 1937 who really described this rigorously and suggested that physical electronic switches could be used to perform Boolean algebra. So this was really, the modern idea of computing. And that same year, Alan Turing publishes his paper on computable numbers, mathematically describing the idea of a universal computer. In 1939, and during this time, there are several tinkers out there kind of working on the idea of computing devices in various forms. And one of those was John Vincent Atanasoff, and he finished a working model of an electronic computer with a kind of mechanical storage device. And Konrad Zuse, working at then Nazi Germany, in Germany, he completed the first fully functional electromechanical computer that was programmable. And at this time, programming was very physical. It was a matter of unplugging things and rerouting cables. The Colossus, this was a vacuum tube-based computing device that was used at Bletchley Park during the war to help crack German codes. And Tommy Flowers, the vacuum tube guy, and Alan Turing were both involved in this. In 1945, you have John Mauchly and Presper Eckert completing the ENIAC. And a lot of people, when you ask what was the first computer, a lot of people say this was the first computer. I think actually Konrad Zuse probably should get more credit for being the first. But Mauchly and Eckert's ENIAC was the first fully electronic programmable computer. And the first real full-time programmers were from this effort as well. Kay McNulty, Betty Jennings, Betty Snyder, Marilyn Meltzer, Fran Bielis, and Ruth Lichterman, 5 female workers in this project were the chief programmers of this instrument. And then, from between during the 40s, during the war era and kind of after, you have this evolution going on from vacuum tubes to more advanced computing technologies. And the beginning of this modernization started with John von Neumann. And he was this huge kind of giant in science. He contributed in hundreds of ways to quantum mechanics and mathematics, and he was involved in the construction of the atomic bomb. But he published a report on the EDVAC and described a stored program architecture. So before this, there was really no concept for stored programs or memory. Reprogramming a computer was a matter of unplugging cables and rewiring stuff. And the stored program architecture was the idea that really is the basis for the modern architecture of computers that have RAM and a central processing unit and separating these different components. In 1947, William Shockley, John Bardeen, and Walter Brattain invent the transistor. And this was a replacement for the vacuum tube, a semiconductor-based technology that could perform the same function, basically provide one signal at one voltage and provide a different signal at another voltage, just a simple 1 or a 0, or true or false, a yes or a no. And in 1950, Turing publishes his test for artificial intelligence. This he's the first to really take seriously the idea of artificial intelligence, and no one else at his time was really thinking about these things. And of course, now we have the Turing test, which was his idea. In 1952, Grace Hopper, so she was working in the Navy. She invented the compiler, which sounds a bit obscure, but it's super critical. The compiler translates human readable code into machine code. So until her time, programming was a matter of working with the ground, electronic logic at the most fundamental level, really working with the ones and zeros and the logic gates that the electronic components are performing. So the compiler was really the basis for modern programming and languages that we have today. And von Neumann, the same year, finishes the EDVAC. So this is the first modern computer with this stored program architecture. In 1954, Alan Turing commits suicide after being prosecuted by his own country for being gay. Really tragic. And Morris Tenenbaum at Bell Labs and Gordon Teal at Texas Instruments in parallel, independently invent the silicon transistor, which, to this day is how we make transistors. And kind of along those lines, in 1958, you have the integrated chip invented by Jack Kilby, being able to print these circuits at really small scale. This is really how computing manufacture started to get automated, and this is the basis for modern computing industry that we have today. In 1966, Bob Taylor gets funding from the Advanced Research Projects Agency to fund ARPANET. And this was the precursor to the internet. Shortly after, in 1969, you have the first nodes installed. So the internet in this time was really just 4 computers connected to each other. But it's grown since then. And in 1971, you have the first commercial microprocessor, the Intel 4004, being manufactured on a large scale and being sold. And from this point on, computers just start to take over the world. You have the personal computer, the Altair, and Bill Gates and Paul Allen, they were enamored with this device, and they dropped out of school and wrote the BASIC language and formed Microsoft. And at the same time, the same year, Steve Jobs and Steve Wozniak launched the Apple I. From this point on, from the 80s on, computing gets increasingly widespread and increasingly powerful and able to do things that people didn't previously ever imagine that machines could do. In 1980, IBM commissions Microsoft to develop the first operating system for the PC, making it more accessible to everyday users. In 91, Tim Berners-Lee announces the World Wide Web. So the internet existed before then, but that was an academic network. Now we start to have the internet being accessible by more people. And that same year, Guido van Rossum and his colleagues launched Python, the programming language that we'll be using. In 98, Larry Page and Sergey Brin launch a search engine based on a clever algorithm, PageRank, named after his name, Larry Page, which eventually became Google as we know it today, but back then it was just a clever way to search the internet. And in 2001, you have Wikipedia, which the wiki technology had been around for a few years, but this is Jimmy Wales and Larry Singer had the idea of this collective encyclopedia, which really not many people predicted that Encyclopedia Britannica would be completely overwhelmed by this. In 2002, you have the first cloud, Amazon Web Services. Of course, social network, 2004, Mark Zuckerberg. Before 2007, Netflix used to mail videos to people, mail physical DVDs to people in the mail, in the post, the postal service. But in 2007, they switched to the streaming service that we know it as today. In 2011, IBM's Watson, a huge computer, wins at the game Jeopardy. And though less people noticed this, in 2012, a few people paying attention noticed that a deep learning algorithm, which had been around for a long time, but nobody had really taken it seriously, but an implementation of this called AlexNet achieved a remarkable success in the ImageNet challenge competition. And then deep learning really started to take off, and that led to 2017 when AlphaGo, DeepMind's deep neural network, defeated the world's top Go player. And to just a few months ago, when DeepMind's AlphaFold 2 succeeded at the CASP competition, crushing all competition. People who had been working on this problem for years, some people who weren't even in this field came and solved this grand problem that had been around for a long time, and nobody expected it to be solved when it was. Yeah. So some really great reading on the topic. So if you're interested in the fundamentals of computing, how a computer physically works, I highly recommend the book based on Feynman's lectures. It's told in a simple, approachable way, and it really shows how computing is, at its heart, a simple idea that's just been taken to an extraordinary height to reach its point today. And he goes through logic gates and logic tables, how to construct simple calculating circuits, basically, and just keeps building from there. And it's all very intuitive and told in very approachable language. If you're interested in the history of computing, I recommend this book by Walter Isaacson. So it starts with the origins that I discussed today, and a lot of this timeline that I've shown you is I've taken from his book. And he goes through everyone who is involved, a lot of interesting personal stories and different personalities. Really quiet people like Alan Turing, who's very shy and really intense, overbearing. William Shockley, the transistor guy, to the lofty John von Neumann, who was thinking 5 steps ahead of everyone else at the time. It's really a fascinating journey, and it's a really interesting read. So that brings us to today. And today, programming is, it's very useful. It's changed the world, we know that. But it's a very practical thing to know these days. And it's easier now it's easier than ever in history to get into it. There's no vacuum tubes involved. There's no punch cards that you have to deal with. You don't need to write in machine code. You don't need to know any electronics. Today we can learn Python. And this is such a clean and approachable language that you will, from your chair and in seconds, be able to do what took dozens of engineers working tirelessly for days to do in the 60s and 50s. So yeah, so here are just some examples. Programming lets you automate things. This is a script, so in my lab, we have a lab notebook, and you upload pictures to it. And this process, if you do it manually, it takes maybe 30 seconds. It's not too demanding, but you have to click a few things. And I wrote a script basically that does this in much less time. You just double click the script and it formats the image. And yeah, it saves time and it's convenient. So this is a very common thing. You'll have some boring task, and you'll just write a quick script to help automate the task and save some time. Another thing is participating in the information ecosystem. So, and using the code of others. So we have, in Python in particular, this huge jungle of different modules or libraries for different things. The pandas library for statistics and data processing. NetworkX is for dealing with network structures and graphs. You have TensorFlow, it's used for neural networks and deep learning. SymPy for symbolic math. Matplotlib for visualizations. Python for interfacing with the C language. And this huge ecosystem. Oh, and I should mention BioPython, which we'll be using for bioinformatics. So this huge ecosystem is, it's not. These are not user-friendly softwares. Like, they're not graphical apps that you can just use. They're programming libraries. So in order to use them, you have to know a little bit of programming just to be able to piece things together. And these are kind of like providing the Lego bricks that allow you to do that. And then there's GitHub. So people, non-professional coders and scientists and people who are not developing full time will upload their code to GitHub all the time. And you have everything from gigantic projects, gigantic open source projects to hobby coders uploading things to GitHub. And these all do interesting, useful things. Well, not all of them useful, but a lot of times you'll find a tool that is available on GitHub, and you need to know maybe a little bit of programming to be able to use it, because it's not it's not a polished software. It's not a commercial application. It's just a library, a set of tools, useful programs, and just knowing a little bit is enough to be able to do so much more by relying on the work that others have already done. Learning. So in my own case, I use Python as a medium to learn things all the time, especially math. And when I first came to Sweden, I wanted to learn the language as fast as possible. And one of these things was, not spending time on vocabulary or words that wouldn't occur frequently. So what I did was I wrote a very simple Python script that parses text. So in this case, I've input the newsletters published by KI into this script, and it's just gone through and cataloged how often each word occurs and ranked them. So you can see "och," the Swedish word for "and," is ranked here at the top, and here it's being plotted. So this was just a quick way to get a list of words that would be important to learn. And you'll find yourself doing this all the time. If you know how to program a bit, there'll be something you wish existed, but you can't. You Google around for it and you just can't find it. And writing a quick script for it solves your problem. SymPy. So you can do math in Python, not just numerical math, but you can do symbolic math. So SymPy is another library, a module. And all you have to do is import it, and then you can start doing algebra and calculus. You can solve integrals. And this is a great way to learn mathematical concepts. It's also a great way to check your math if you're doing this for research. And it can be a good way to explore and play around as well. Devices, so electronics electronic hardware. So these days you have things like, this is a Raspberry Pi, it's called. So just a very cheap, a cheap computer that you can plug into hardware and use as a microcontroller. And it's running a simple Linux-based operating system, and you can run Python programs to control hardware. So in this case, we have a blue LED that's being controlled. The frequency of its flashing is being controlled by a Python program here. And there's lots of more complex hardware projects that one could do with Python programming. Another super useful thing is simulation. So simulation, it sounds very complex and fancy, but most of the time simulation is just using random numbers in a clever way. So a lot of scientific questions are easier to estimate using random numbers than to derive analytical expressions for. So what do I mean by that? So for example, consider this problem. So we have a bunch of black dots and a bunch of red dots. And let's say we know the density of randomly placed black dots and randomly placed red dots. And we just want to know for a random scattering of these, a random distribution of these, which fraction of pairs land within a certain distance of each other. Like let's say we have a distance X threshold, and we want to know, how many of these pairs are within that distance. It seems like a pretty hard problem, and there is a mathematical approach. So you can use calculus and probability theory what you have to do is you start with what's called the nearest neighbor distribution. And from that, you can derive an expression for the probability distribution of that satisfies this condition. But this approach is not always obvious, and there are tons of problems where you're not necessarily going to know how to do this unless you're a mathematician. But being able to program this problem can be very simple a lot of times. So in this case, all we have to do is generate two sets of coordinates, one for the red and one for the black dots. And generating a coordinate, is as simple as telling the computer, pick a random number from 0 to 15 as a y value, and a random number from 0 to 15 as our x value, and that's a random point. And you just have a list of these basically, and you go through each of them. And if you remember from geometry, there's the distance formula that you can use to measure the distance between 2 points in space. And you just do this for thousands of points. This is the Monte Carlo approach, basically. So using random numbers and large numbers, basically, to compute these distributions. And there you have your solution. And we didn't need to really know any of this high-level math to get there. So that's super useful. Another thing in scientific programming is processing images. So this is a picture of a cancer cell that is expressing HER2, a protein that's being expressed in the membrane. And it has a tendency to form these clusters. And what we wanted to know in this case was what were the size of these clusters? What was their distribution? So we did this very high resolution microscopy technique called DNA paint. And we produced these images that we could analyze to kind of to assess the size of these individual clusters and produce a statistical distribution here based on the image. Visualization is really important in science. So a lot of times you'll compute something and you want to find a beautiful way to express it or to show it, and especially for publication and disseminating your work or your research, being able to visualize data in an effective way is really important. And a lot of times that means going beyond the Excel bar graph with error bars, and Python has several libraries. The main one is probably matplotlib that you can use to generate almost any kind of visualization that you can conceive of. And these are from my own work here, and we'll use this one in the middle here soon for visualizing alignments in bioinformatics. But it's very easy to use on a basic level, but it's also very deep, and you have a lot of freedom with it. You can go quite far. So increasingly, programming is advantageous for doing science. So you'll find that it's first of all, it's free. So you have a professional caliber of capability here that is free, and it can be a way to leverage. It can be a way to leverage your abilities, because you need a huge budget to do research these days in a lot of things. If you want to build a protein, or if you want to do animal experiments, these things cost a lot of money. But programming is one thing that you can reach the highest level for free. And this isn't true for a lot of other things. Programming in MATLAB costs money, for example. And yeah, so it's increasingly important to know how to do it. And being able to reproduce others' work, for example, a lot of times you'll run into a tool that someone has made, and it will be really interesting to you or really important for the thing you're doing. And in a lot of experimental science, it's very hard to reproduce other people's work. It costs you a lot of resources to do so. But programming is something much more accessible. You can reproduce other people's work in programming oftentimes much easier than experimental work. And yeah, just being able to make any kind of tool, having the freedom is really important. And in the last few publications that I've been a part of, Python programming, making tools, has been a part of that. The Python programming language itself has become increasingly prevalent in science. So the reason is it's a fast prototyping tool. So in science, you tend to care less about the raw power a lot of times, and certainly you care less about the polish. So a lot of software development out in the world is making software for other users and making it look nice and making it commercially viable. But in science, a lot of times you just want to solve a problem for yourself, and you want to know the answer like today, and not have a 2-year project. So Python is a really good language for that. It's less focused on end product software, and it's more useful for visualizing things and inventing new algorithms, like doing actual programming and inventing algorithms. Another reason that it's becoming more prevalent is because it's got a huge community. So it's this open source project, unlike MATLAB or Microsoft Excel. And the community of contributions have sort of gone beyond the threshold at this point. So like most scientific computing problems have an equivalent Python library. And if you're in a particular field, like bioinformatics, you have a Python package that's available to help you with it. How about compared to other languages? So Python is what's called an interpreted language. And this means that commands are executed by an interpreter, which takes the code you've written and translates it in real time into machine code. And that means that time is spent on this translation process during the running, and it's slower as a result. So the trade-off is that the syntax is easier to learn. So it's what's called a high-level language, and the syntax is written in an easy to understand, kind of intuitive sense. And that's in contrast to languages like C++, C, or Java. And these are compiled languages that are closer to the machine. You're performing more kind of basic steps, basic operations yourself when you're coding in these languages. But these tend to run much faster, but they also take longer to code in, and they're harder to prototype in. So oftentimes people will prototype in Python, and then if they need to, they will move their code to a language like C++. The other thing is Python is a general language. So some languages are optimized for certain tasks, and it can be worth using those languages in certain contexts. But Python is fully general. So you can do, symbolic math with SymPy, do some algebra, and in the very same program, create a data visualization, and and all this is a web application that you've made, and it's interfacing with an operating system. It's fully general, and not all languages have this benefit. In industry, pretty much everyone is using it. So Google has said Python where we can, C++ where we must. What they mean by this is that Python is, it has the lower barrier to entry. So you should use it as much as you can. But in cases where performance is a priority, then Google will use C++. And Python is one of their official languages along with C++, Java, and Go. And other companies, Spotify uses a combination of Python and C++. Reddit, Steve Huffman, one of the Reddit founders, is quoted as saying, "There's a library for everything." We've been learning a lot of these technologies and a lot of these architectures as we go. And so when I don't understand connection pools, I can just find a library until I understand it better myself and write our own. Don't understand web frameworks, so we'll use someone else's until we make our own. Python is an awesome crutch like that. Steve Huffman. So that's often how we're going to be using it. And this is also kind of what I was saying about learning things. Like maybe I don't know, how alignments work for DNA sequences. Maybe I will then use the BioPython package to do some alignment, without fully understanding it first. And it can be a great way to learn, what is the essence of alignment before going into the gritty details. So for master's level bioinformatics, you should be able to explain and describe theories and methods that are used within bioinformatics. You should account for how bioinformatics methods are used within biomedical research. You should also be able to use bioinformatics technologies and analyze bioinformatics data appropriately, and critically assess and evaluate which methods should be used to solve specific bioinformatics issues. And basically all of these things are going to benefit from us being able to program a bit, because as it's conducted today, bioinformatics is mostly programming, and it is making your own tools. And being able to critically assess or evaluate which method you should use. This is really something that, in order to do it, you have to understand these algorithms from the inside out. In order to understand algorithms, it really helps to know how to make them as well. So there are all sorts of tools out there for doing bioinformatics. Clustal, Omega, UniProt. Most of you have probably used BLAST from NCBI, Muscle, but things for doing hierarchical clustering, phylogeny, motif searching. But there's really, it starts to become difficult to teach all of these things. So yeah, you can see from this plot that the number of tools is growing exponentially. This is not showing any signs of slowing down. Here's this pie chart is kind of breaking down different sectors in biomedicine. And here we have high throughput sequencing, for example, is like a really big area. And, this is a log scale. So things are getting more and more heavy with the number of tools. And we just can't teach you tools that are going to be useful for that long. So yeah, we can say this: learn to use a tool for a day, learn to make tools for a lifetime. And here you can see the number of tools by programming language. And yeah, of course, these tools, they're made in a particular programming language. And you can see one of those is Python. So we might as well learn one of these languages, and then we can start to make our own tools. And this will be much more enduring and sustainable knowledge in a field that is changing so quickly, rather than just learning a few of these tools that maybe are useful today but out of date tomorrow. So to do bioinformatics, we shall learn to program. So what should one know already? Do you need to know programming already to start learning bioinformatics? I would say no. We're going to learn from the bottom up, and these days it really does not take much effort to get into programming. Like I said, there's no punch cards, there's no vacuum tubes. It's going to take us a few days, and you will already be flying. You will want to know how to program to be competent in bioinformatics, and that's the goal of this course. Will it be hard? Not as hard as you think. So with that, I'll end here, and in the next video, we'll discuss the basic elements of programming in Python. And I'll show you how you can get started immediately with almost zero hassle. And we can start to learn some of the basic things that we'll need to do bioinformatics. So cheers, and see you next time.